integration. Now, whenever you're learning calculus these days, you always learn differentiation first and integration second, because they're opposites of each other, and integration is harder. In the same way as when you started school, you learned to multiply before you learned how to divide. Okay? But interestingly, I don't know if you remember from our differentiation unit that we said that differentiation was discovered or mainly looked at by Leibniz and Newton, which is like 16th, 17th century. It's a while ago. But if we teach that first, because it's the leads into, you would think integration would have been found after that. But integration has its roots way back to the Greeks. So one of the applications we're going to find out with integral calculus is that we can find areas under curves. And so far, areas that we have been sort of limited to with our geometries, like, ooh, we can find the area of a square, right? We can find the area of a triangle. But if I had a parabola and wanted to find this area, it'd be tricky because of that bend. And integration is going to be an application for this. And it comes back to Archimedes. Archimedes was one of the first mathematicians to really look at pi. He is called the father of integral calculus, and this sounds wonderfully tiring. He developed a method of exhaustion. He is like, if I wanted to find this area under this parabola, I could estimate it by using one big rectangle. And it wouldn't be very accurate. However, if I picked a point in between and instead did this small rectangle and this rectangle, that would be more accurate than my first guess. And then if I made the rectangles smaller, it would be more accurate than my second guess. And smaller again, until I get infinitely small rectangles, and I can get what is the area of. In fact, just a story about Archimedes, okay? Some stories about Archimedes. First of all, Archimedes, he is able to find pi as close as he wanted to with his method of exhaustion, okay? And he was able to then, because he could find pi as close as he wanted to, he was able to correctly get the circumference formula as 2 pi r. And it was Archimedes who was able to correctly realize that if pi is in your circumference formula, pi also has to be in your area formula. I don't know if you've ever wondered that, like, how does it that it's pi in both of them? Like, why does that work? And so what Archimedes did with his circle is, he's like, imagine you had an orange, and you did a slice right through the center of that orange, and it would sort of look like this, right? A bunch of slices or sectors. And if you opened up your orange at one end and laid it out flat, sort of as flat as you could, it would look like that, okay? Now, if you made your sectors smaller, they would get closer, tighter and tighter together. And as you make them smaller and smaller, they become more like triangles. Agreed? Dot, 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 dot. And you would have a row of triangles that would have this length exactly the length of your circumference. In fact, the smaller you make your triangles, the more this bumpy part would become perfectly flat. And if you did it forever, eventually it would be a perfect straight line with a length of 2 pi r. And if I took two such orange slices and did one orange slice like that, and then took the other orange slice and filled in all of the gaps with that one, I would eventually get a rectangle. And that rectangle, if you went infinitesimally small, your triangles would eventually become almost like lines that are straight up and down. And what is the height of one of these triangles? Is r. And the area of this rectangle is 2 pi r times r, which would be 2 pi r squared. But that's putting two circles together. So to find the area of one circle, all you'd have to do is divide by 2. That's pretty fascinating, right? Thinking of these area questions way back, this is all over 2,000 years ago already. So that's Archimedes. So what we're going to be looking at is that antidifferentiation, or the indefinite integral. That's undoing the derivative, the reverse process. Okay? So if you had the derivative was 2x, then you could say, what would my equation have been originally? It would have to be x squared. But it could be x squared plus anything. I think this is where we use plus 13 for the longest time, right? Is that the number of choice? I think it was. And then plus c says there could be any number there that would work. So this is called the integral. And we always have to write that plus c to indicate that there's more than one possibility. Some notation, right? We had our notation for derivatives. Okay? Here is our notation for finding the integral. It's the integral sign. It's like a long, skinny S. Okay? Inside, we call it the integrand. X is the variable of integration. And then afterwards, the plus c is your constant. So in an integral, we always have this dx, and that's sort of the indicator which variable are you finding the integral with. Okay? Sort of like with derivatives, we always had that take d dx, means take the derivative with respect to x. When we did related rates, we always did d dt, because we were taking the derivative with respect to time. So we show that in the same way in integrals with that notation. Here's just a little flow chart, right? You have one function, you do the derivative, you work backwards. They like to use the capital f of x if you're going backwards to, like, if you started with f of x. If you started with f of x and went backwards, you go big F of x. Oh. Bold f of x. Double bold f of x. Yeah. Start with yeah. You start with a sans serif font, and then you add the serifs. Those are the little things on the fonts that make them fancier. I don't know. Perfect. Yeah. Okay? So we have to review our derivative rules in order to work backwards. You have x to the 5. What's your derivative rule? Right? Bring the 5 out in front and then subtract 1 from the exponent. So now we need to undo that. Now, most of the time, right, if I gave you one like this and asked you to undo it, it's not hard for you to see, oh, it was x to the 4, right? Because you said, oh, the number comes back out in front and we add 1 to the exponent. But sometimes our math is going to be such that we need to undo it a little bit with more steps and sort of more of a process. So if the process was bring the number in front and then subtract 1 from the exponent, that's going in this direction. And if the derivative is going in the opposite direction, you would undo them in the opposite order. So if the last thing we did was subtract 1 from the exponent, the first thing we would do is add 1 to the exponent. And if the first thing we did was multiply by the number in front, we now would have to undo that. What's the opposite of multiplying? Dividing. So if you had something where the numbers weren't easy, and you had to undo it, you would start by saying, originally, I would have had 1 more on the exponent. Originally, I would have had 9/5. And then if I did the derivative, that 9/5 would come out in front. So to undo multiplying by 9/5, I'm going to have to divide by 9/5, and I still would have this 2/3 in front. Now, 2/3 divided by 9/5, you know how to divide by a fraction. Dividing by a fraction is multiplying by the reciprocal. 2/3 times 5/9. And that's working backwards. Whereas this one, I think you'd all agree, that was easy to do mental math. Here, with the fractions, not as easy to do the mental math. Not as easy to see, oh yeah, definitely a 10/27 in front. I saw that right away. Okay? But if we undo it by thinking of the opposite operations, you now have a method. Okay? I will first add 1 to the exponent and divide by that exponent. And then I can do the mathematics for simplifying if I need to. And so those are the steps. Some of these we could do directly. If you were showing the steps for this one, you would add 1 to the exponent and divide by the exponent, which ends up simplifying just to be x to the 5. Originally, you would have just been able to see that and said, no problem, Mr. JR, it's just x to the 5. I can undo that one easy in my head. Okay? Same thing, you probably could undo this one fairly easy in your head. But now as a technique, keep my 12, add 1 to the exponent, and divide by my exponent. And you'll actually find when you're in the midst of more difficult questions and you've got to integrate, it's nice to have something simplistic to do. Just add 1 to the exponent and divide by my exponent is a lot simpler than saying, okay, it's going to be what would have to be in front. You have to like derivative and at the same time. Now we have a technique that allows us to find it quicker, right? So undoing the steps, we're going to add 1 to the exponent, divide that function by that new exponent, because that's the opposite of what the derivative would do, and then everything works out fine. And then, when you're integrating, you're going to always add c to show that there could have been a constant. So just like derivatives, we start having some integral rules. Oh, no, it's nice. Here's our integral number 1. Can you see that this is just adding 1 to the exponent and dividing by your new exponent? This is exact opposite of your power rule for derivatives. But then you have the plus c. And does it make sense that n can't be minus 1. Because then you would have to divide by 0. Okay? And if there was any number in front, which we did some of those already, like the 12 that we just did right here, you just keep the 12 there. Add 1 to your exponent and divide by your new exponent. That value doesn't affect it. Okay? So these are generalizations of the rule that we just saw. Again, you will find that you'll be able to do these rules because we do a lot of them. Okay? Give it a try. Sometimes. You can if you'd like. You can draw. I like it even skinnier. Yeah, I like it a really long F without the middle thing. Add 1 to the exponent and divide. And then you don't have to write the CER. You can just write plus C. But it just is indicating that C could be any real number. So remember when I said in derivatives you were going to get really good at subtracting 1? Now you're going to get really good at adding 1. Like, it's like skills that you can use. So when it says integrate with respect to x, this is how you'd write. I'm integrating. You could write f of x or x to the minus 3 here, but you have to write the dx to say that means I'm integrating with respect to x. Add 1 to the exponent and divide by your new exponent. And so getting good at original derivative rules will imply the same things for our integral rules. This one, there's a typo. There should be a dx here. And with derivatives, if you had a square root, you changed it to an exponent. Does it make sense? And integrals will do the same thing. We have an x to the half. So what are we going to do? Add 1 to our exponent and divide by our new exponent. Then you have a fraction inside of a fraction, so we have to multiply by the reciprocal. And it simplifies nicely. Okay, so I'm going to save you some. You don't have to write. You can just write plus C. That's fine. Try the next one if you haven't already. You have to change that. You have to change that to a 3/7. Is that 3/7 is hard to see. Okay, that's a good question. So why does it say y dx? So this means find the integral of y with respect to x, but there is no x's in this. But we have an equation that says y is equal to this, so I could substitute this in to be x's. So the dx is telling you what variable you should have in your equation, because we haven't learned anything that's equal to implicit differentiation for integration. So what we're going to always try to do is whatever is listed as the variable that you want to find, the integrand should be in that variable. How did your adding 1 go? Save you some time, don't write that. And then okay. So all of our integration starts off with our easy derivative rules, and then we advance from there. Generally speaking, working backwards is harder than working forwards. And that's true for all math. Dividing was harder for you than multiplying. Subtracting was harder for you than adding. Factoring was harder than you than distributing. Okay? In fact, some factoring is so difficult that they have huge prizes out there for it. Have you ever seen the RSA factoring challenge? Oh, okay. It's worth having a look at. If you don't mind me getting off topic for a little bit. Okay. So, for those of you that like computer stuff, okay, a lot of cryptography and a lot of password protection is based on numbers. And when you provide a password, you provide a key that gets checked, and if that key is correct, then it opens up the lock. For the most part. This is simplistic ideas of it, okay? So if we break that down to factoring, the key would be I tell you a number, okay? Here's a good one. I tell you 899. You give me a password, and if it's one of the factors, I open the door. 3? No, 899 does not divide by 3. 47. It's not 47. 1. Well, and 1 and 899 are the basic ones, so that would never be, it's got to be one of the actual factors. Now, I chose 899 because it's the product of 2 prime factors. If I had chosen 898, it would be really easy to figure out that you could divide it by 2 because it's even, right? If I had chosen 897, it would be really easy for you to say that's divisible by 3 because of the divisible by 3 rule. 8 plus 9 plus 7 adds up to 24, and since 24 is divisible by 3, so is 897. Okay? But 899 is 29 times 31. And 29 and 31 are both prime numbers. So if you were guessing and checking as you went along, 2 doesn't work, 3 doesn't work, I don't have to try 4 because 2 didn't work. But 5 doesn't work. 6, I don't have to try because 2 and 3 didn't work. And you'd go up, and eventually you would have found 29. This is the basis of the RSA factoring challenge. They provided big numbers and cash prize money if you could factor them. So here are the numbers. Okay? Here's the very first number. It had 100 digits, and if you factored it, you won $1,000. So the first person that factored it won $1,000. Okay? Lenstra factored it. He started working on it right away. He got $1,000. And you were allowed, you could use calculators, computers, whatever you wanted. Okay? In 1991, he factored it. Okay? You want to see how big the number was? right? You thought 899 was hard? That's the number he had. Okay, that's pretty big. And no, here's the answer. This number times this number, and both of those numbers are big prime numbers. Very big prime numbers. Okay? The story behind the RSA factoring challenge is they got a computer to multiply big prime numbers together. They wrote down the answer, then destroyed the computer so nobody knew what the answers were. And so it was legitimately, we don't know the answer to these, but there is an answer. And once you find two things, it's really easy to check. It takes a computer less than a second, less than a millisecond to check if that's right. But it takes a very long time to find the two answers that work. So we go back to the table here. Oh. Look at this. Compared to the one with 140 digits, that took 8 years longer. And when we see 8 years longer, we know that Lenstra had a computer program, because once you set up a computer program, if you want to win this prize of $17,000, you just let it run, right? You don't have to do any work. As long as you get an answer before somebody else, you'll win the prize. Okay? Now, why would RSA just give money away for factoring, right? Your grade 9 teachers never did that. Like, it would be nice, eh? Welcome to grade 9 class. Here's your assignment. First person to get it done gets $5. Right? And then you'd be, I'm going to drop this course right at the end and take it again next year to make more money. But the crazy thing is, okay, first of all, why did they do this? Okay? Well, if all of a sudden somebody started to figure these things out faster, developed a new algorithm, they potentially could break into high security banks and different things because they could surpass their password easier if they had the mathematics to do it. So by creating this challenge, they were more than happy to find out someone like Arjun, hey, we should hire this guy. He's finding out fast ways to do it, but we're also quite happy that it took him an extra 8 years or 5 years from the first one to get the second one. You know, he's outside the bank, and 5 years later, he's still trying to, okay, we're not too worried about him breaking in, okay? So if we change our password every 4 years, we should be good. Right? And look at some of these ones that are still to be, look at how many never got solved. Yeah. Now they've taken away the prize money is now, I think, rescinded. So the prize money that was there is no longer available, but $200,000 if you could factor that. And if you could just get a computer doing it off to the side, you could claim that money. Okay? So we're going to find the connection here is in integration, it can get difficult to work backwards because it's harder than working forwards. I sometimes tell the analogy of my ex-neighbor who passed away a number of years ago. He was very particular. And he was, okay, a little story about my ex-neighbor. Probably suffered from some mental health issues with OCD and stuff like that. When we moved into our house, this was 16 years ago, we moved in winter, and I would say, he was retired, I would say he shoveled snow on an average of 5 hours per day, whether it snowed or not. Okay? So when you've shoveled most of your snow away, you have to find more snow to shovel. So this includes, like, he had the most beautifully shoveled yard that you can imagine. There was like no snow in his whole yard. He would even brush off branches, brush the snow off branches so it comes to the ground. And when he would shovel his snow, it was very methodical. This little pile, he would take a scoop of snow, lift it up and dump it, making a, it could be a related rates question, a perfectly conical shaped snow pile. Then he would go from the bottom to the top, let it fall down the other side, and this cone would slowly get bigger as it traveled across his backyard, and then in his front yard, another perfectly conical shape of snow, and this little cone would go up to the top of that and then spread down. One day I saw him shoveling his roof. You would think the normal way that you would shovel the snow off your roof is you would be like, roof is dangerous, get all the snow off onto the ground first, and then shovel it away. But instead, the little conical snow thing went up over the top of the roof, down the other roof, onto the ground, and then and up onto the main cone shape. So I was like, what is he going to do in summer? Right? Because there's no snow. It's like, how are you going to fill your time? Now I found out in summertime, see, first of all, you have to understand the purpose of all of this, okay? There is a logical reason, because I was up, like, I tried to figure it out. I'm like, I do not understand why you're shoveling so much. Well, his property is the lowest property of all the neighbors. So when the snow melts in spring, or when you get a torrential downpour in spring, and you have flooding, where does the water go? It goes to the lowest spot. So all the water in the neighborhood goes to his yard. And then he gets water in his basement. So in order to avoid having water in the basement, if you move the snow away all winter, less will melt, less puddles will happen, better chance to not have water in the basement. So that made logical sense, and it also made logical sense for the summertime, because the summertime, sorry, this is a long story that's going to get to connecting to this in a bit. Okay? In the summertime, he had a huge pile of dirt delivered to his front yard so that he could put that dirt in the backyard. If he put dirt in his backyard would be higher, and then the water wouldn't come to his yard because his yard would be higher. Okay? Problem with the dirt is that it had stones in it. So before he put the dirt in his backyard, he needed to get the stones out of the dirt. And this is my connection to factoring and working backwards. How long would it take you if I gave you a pail of dirt and a pail of stones? How long would it take you to mix them up? Not that long, right? Activity number one, okay, mix them up. Activity number two, okay, I need to do this activity with my next class. Could you put the stones back in here and the dirt back in this pail? It'd take a very long time. And yes, he sifted it. He had a sifter. Sometimes you would look out at night at 2 o'clock in the morning, he had a miner's light on. He would be sifting dirt in the middle of the night. And one time I was trying to fix a hole, and I had some dirt with some stones. I'm like, well, I'll ask my neighbor. He's got a sifter. What could I borrow his sifter to make it a little? His sifter he used was a window screen. So any stone that's bigger than, you know how fine a window screen is? He would sort that out. I mean, he had some of the finest dirt in his backyard. Unbelievable. Okay.
What happened to the snow cones? Like, he put them in his front yard, then what?
Well, he made one big cone, and then in spring it would melt, but it would melt near the street so that it would go away that way. Okay, so more integration rules, because we're going to be working backwards. We're going to be taking stones out of dirt. Craziest thing that ever happened with our neighbor. One morning I was going out to bring recycling out on recycling day. Beautiful summer day, not a cloud in the sky. And all of a sudden I'm getting rained on. And I cannot figure out, and I have somewhere in the depths of our computer memory, I have a video of this, because I was like, this is the craziest thing that's ever happened to me. I'm getting rained on in the middle of a summer day with not a cloud in the sky. I look up, And if you go past our house, there is a very, 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 very tall pine tree in his backyard. And attached to the pine tree, to the very top of the pine tree, he had attached a garden hose. A very long hose. If this is a 20-foot ladder, this is the perspective. There's the 20-foot ladder. He had to go up about a third of the tree, that's how big the tree is, and then climb the rest just by branches, bringing the hose. He attached the hose to the top of the tree. I have video of a very big tree with water shooting out the top of it. Okay? And, Michael's like one of the puzzles you bring in. I thought, right? Because the shoveling snow and the sifting dirt, they all had a reason. And I tried. I could not figure it. I was like the puzzle, I could not. Finally, I went to him, I said, okay, you have to explain to me, why is the hose attached to the top of the tree? And he said, well, yeah, well, it just attached to the regular garden, it had enough pressure to shoot it all the way up. He said, well, there's a squirrel in my backyard. And I want to get rid of the squirrel. So I chase the squirrel, and what does the squirrel do? Goes up the tree. And if it goes up a pine tree, it's going to wiggle and knock pine needles down, which is like, it makes a mess. You have to sweep up pine needles. You know that. So this was a problem. Couldn't get rid of this squirrel because it would always go up the tree. So squirrel goes up the tree. He turns on the tap. Squirrel's like, I don't like getting wet. Comes down, he's able to throw one more stick at it, and hopefully it goes to the neighbor's house. So, all right. He's got a plan. All right, back to integrals. Just like derivatives, if you're adding two derivatives, you could take the derivative of each one separately. You can do the same thing with integrals. If you're adding inside of the integrals, you can find each one separately. So what does that mean for us? If you have something like this, I can find the integral of x to the 5 on its own. I can find the integral of the minus 3x on its own, and the integral of a 2 on its own. I'm not happy with my integral signs. I want to make them skinnier. Here we go. Here we go. And then our rules of adding 1 to the exponent and dividing can be applied to each one of them. Add 1 to the exponent, divide, add 1 to the exponent and divide, add 1 to the exponent. And if you have a constant, does it make sense that you would just have a 2x? Because if the derivative of 2x is just 2, then if you have a 2, you just have 2x. And again, if you don't want to, you could just write plus c. When you write plus c, everybody is aware that you mean everything. So just like derivatives, we sometimes have to do a little bit of work before we get it into a form we can integrate. It's not so bad. But you're just foreboding doing lots of work for some? So if I multiply this out, then I can integrate each one separately. Add 1 to the exponent and divide. Add 1 to the exponent and divide. So far, that's our only thing that we have. And we're going to find that you're going to develop more integral rules to allow you to do things, which makes life more difficult because the more things you have available to do, the more difficult questions are, right? So we've got our helpful hint here that says you need to rearrange things to get it into a form that you can work with. This is in a form that you cannot work with. What do you have as an idea? We don't have a quotient rule for integrals. The inverse quotient rule. We can factor. So if we factor, the top factors out nicely, the x minus 2's disappear, and now y is just x minus 4. So if we want to find the integral, add 1 to the exponent and divide, it works out nicely. Try the next one. All right, how did you do? Did you change the cube root to 1/3? And then add 1 to the exponent and divide. So here you have a fraction within a fraction, so then you can multiply by the reciprocal to simplify it. Always remember the plus c. So these are called indefinite integrals because they never have a definite answer because it always has the plus c. We will do questions with definite integrals as well. So there are indefinite integrals and there are definite integrals. Right now, so no matter what function you have inside, if that function is multiplied by some constant, some number, you can pull that number out in front and just do the integral of the inside. And we saw this with derivatives as well, right? If you had x cubed, your derivative was 3x squared. Did it make a difference if you put a 5 out in front? You still had the 3x squared, but now it got multiplied by the 5. We just did it all in one step and wrote 15x squared. But it didn't make a difference that that 5 was there. Same thing happens with integrals. The fact that there's a 4 there doesn't make a difference for the derivative, doesn't make a difference for the integral. Okay? But it is true, as soon as you learn something more, not only does that complicate things because you've learned something new, but now you've also given your brain an opportunity to mix things up. So you have to take a step back and add focus, right? What's my rules for derivatives? What are my rules for integrals? Sometimes you add, sometimes you subtract. And so your brain's going to want to play tricks on you and go like, oh, what'd you do this time? So first of all, I probably change my f of x to 4x to the minus 3. And then in the derivative rule, bring the number out in front and subtract 1. So we get negative 12x to the negative 4. For my integral rule, I can bring that 4 out. I don't know if I would necessarily expect, I don't think I'd even ask you to show that. Because what do? Add 1 to your exponent and divide. Would it have mattered that you brought the 4 out? Probably not. But there are cases where it's easier to see what the final answer would be. By doing that. Okay, 2 more for you to try. Try the example 2 and the example 3. It doesn't, yeah, you don't need to, but it is a rule saying you can if you want to. But it's not necessary. You wouldn't have to bring the 4 out. You could leave it inside. Oh, I have a typo on this one. I'm missing the dx. What's the derivative of 20? Not x. Uh-oh. I put the third one in there as a little bit of a challenge. So far, the good thing about that third one is no one's got it. Wow, it means there's opportunity to learn as a teacher. Isn't that the most? That's what I'm looking for. Oh, and it is possible. Oh. How'd this one go? Change this first? No? Oh, we got somebody. Nope, that's wrong. Thought somebody had it. No, oh. Man. Okay. Oh, don't give it away. Oh, can I do this one? Okay, so on this one, you would first take that. First take the u to the fifth root of u and change it to u to the 1/5. I can take the 30 out in front just to keep things simple. And now the integral says add 1 to the exponent and divide. So I add 1 to the exponent and divide, multiply by the reciprocal to simplify, and I get 150 over 6, which reduces to 25. Again, that is our first one. But then we got to the second one that is causing people trouble. Everybody done on this one? Yes? So, and you wanted more time? Or do you think you got it?
And now I've given up.
You've given up. Perfect.
It's because it's impossible.
It's not impossible. So
In our rules, that we have no formula for it. Yeah, we have no formula.
I'm going to bring the 20 out in front because I can do that.
How dare you?
Okay. I'm going to take that 20 out in front because I think in this one particular, it might help you. Okay? And I'm going to write it like this. I'm going to say, thinking back of derivatives, I have f prime of x equals, and unfortunately, I got there was an ink blot, so this you couldn't really see it very well. But I did my work, and I said, oh yeah, I remember the rule for the derivative, the derivative of this is 1 over x. What? The natural log. Okay? And so if I'm working backwards and I have 21 over x dx, the answer is going to be 20 natural log of x plus c. Okay? And this is where integration is hard. Your brain,
Pretty sure that's wrong.
you don't like it? Oh, you checked Alice's. It's not what Alice got, so I must be doing it wrong. You're right. I understand. Yeah, so it's interesting how our brains are, like, if I gave you this at this moment, lots of you would have no problem saying, oh yeah, derivative of ln of x is 1 over x. And your brain is trained to trigger something in one direction, right? I don't know if you've ever noticed when your brain does this to you, but when you have a trigger, you go to the next step and it's no problem. But sometimes if they take that trigger away, and I just give you the answer, it's like, I now have no ability to do this. And it's fascinating how hard that is for our brain. In fact, the only thing you kept doing was this, right? Okay, I have x to the minus 1. I need to add 1 to the, add 1 to the exponent and divide. And so I just want to say it's not possible, right? Because your brain was going to that trigger instead of recognizing the ln x. Fascinating. So exciting. Okay. Another general result is if you're finding the integral of a derivative, does it make sense that you would just get the original equation to begin with? Because they undo each other. But you would have to write a plus c. So here we have an interesting notation thing. The notation says find the integral of the derivative of 5x squared. So if you were doing order of operations, you would first have to find the derivative of 5x squared, which would be 10x. And then how do you find the derivative of 10x? Well, you would add 1 to the exponent and divide. And if you simplify that, you get 5x squared. Whoa. You don't have to write that. That's fine. Can you see that integrating and derivatives, since they undo each other, okay, since they undo each other, they cancel each other out. But not completely cancel each other out, because I still have the plus c. Okay? Hey. But this is different. A little bit. Can you see in this one, when you integrate a derivative, they cancel each other out, but you would have the plus c. But if you differentiate the integral, doing the integral first would cause you to have a plus c. But then when you do the derivative of that, you'd get the original back how you started, and then the derivative of the plus c would be 0, because the derivative of any constant would be 0. So there's a slight difference. They do cancel each other out. So I have no problem that you would say, hey, these cancel each other out. I'm going to get 5x to the minus 3 as my final answer. But you have to know, is this the one where I would have a plus c? Or is this the one where I don't have a plus c? And it all depends what you do last. If you do the integral last, you'll always have a plus c. If you do the derivative last, well, the derivative of any constant is 0, so then you wouldn't have a plus c. So there's some questions there at the end. You can pull out your textbooks and start working on those.